Welcome to Video 3, where we define our battleground, hypothesis formulation. We start with the null hypothesis, H0. Think of this as the shield of statistics, the default stance of skepticism. It effectively states, nothing has changed. The observed difference is just noise. In the legal system, a defendant is innocent until proven guilty. In ML engineering, a new model is useless until proven effective. We see simple arrows labeled as claims bouncing off the shield. Without strong evidence, the status box remains firm. Observed difference is noise. We never try to prove the null is true. We assume it is true and see if the data forces us to abandon it. Opposing the null is H1, the alternative hypothesis. This is the challenger. This represents the outcome we hope for. The effect exists, or Model B is better than Model A. Visualized as a scale, the burden of proof rests entirely on H1. The scale starts tipped against it. Only when we pile on enough data, represented here by heavy evidence blocks, can we tip the scales in favor of the alternative. If we don't have enough data, we default back to the null. We don't say the null is true, we just say we failed to reject it. It's a subtle but critical distinction.
Hypotheses have direction. A two-sided test checks if A is not equal to B. This cares about any difference, whether the new model is better or worse. The rejection regions are split between both tails of the distribution. In contrast, a one-sided test checks if B is strictly greater than A. Here, all our statistical power is focused on the right tail. In ML product launches, we often use one-sided tests because we only care about shipping improvements. If the new model is worse, the action, don't ship, is the same as if it were equal. However, one-sided tests require caution. You must be willing to ignore extreme negative results.
Finally, the golden rule of hypothesis testing in ML, write it down before you look at the data. We call this pre-registration. This means explicitly defining the experiment plan, the metric, the hypotheses, and the sample size. Once the plan is set, we lock it. Why? Because if you change your hypothesis after seeing the results, for example, switching from conversion rate to time on site because that looks better, you are cheating. That is called p-hacking. It invalidates your p-values and leads to shipping bad models. Using a rigid experimentation framework prevents this and keeps your engineering honest. If you found this video helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.